In Chapter 2, Section 6, we're going to be looking at combinations of functions, composite functions, and domain restrictions. So we've looked at domain before. We've interpreted domain from graphs. In this lesson, this section, we're going to be looking at finding domain from equations and not graphs. All right, so we're going to look at some graphs to help us understand what we look for in the equations, but basically, given an equation, let's find the domain instead of looking at a graph. So we're going to start with domains. We're going to look at three types of functions. We're going to look at polynomial functions, like a line or a quadratic or a cubic. They all have an unrestricted domain. And in interval notation, their domain would be reported as negative infinity to positive infinity, meaning all x values, all real numbers are part of the domain. So polynomial functions, anytime we see those types of graphs or equations, we have to be able to identify them. We know that the answer to the domain question is all real numbers. We're also going to be looking at rational functions and even root functions. So we've got three functions we're responsible for knowing how to find their domains. Rational functions and even root functions have restrictions on their domain, meaning we're going to have some kind of break in all real numbers, some kind of x values that we have to remove from the set of all real numbers. So just kind of briefly looking at what a rational function's definition is and an even roots function's definition is, and then I'm going to go to an additional worksheet to kind of look at those types of functions. This is where we're going to struggle the most, finding domains of rational and even root functions. All right, so a rational function is always in the form of a fraction. And when we think of fraction, we might want to think about the word ratio. And when you think about that word ratio, it begins the word rational. So a rational function is always in the form of a fraction. When there is a variable in the denominator, not the numerator, for the domain question, all we focus on is the denominator for the domain question. So when there's a variable in the denominator, there may exist some value, some x value, that will make the denominator equal to 0. And we don't ever want a fraction to have a 0 in the denominator. That's just kind of a bad thing in math. We don't divide by 0. It doesn't make sense. So, and that value must be restricted from the domain. Just a real quick example here. It says f of x equals 1 over x. Well, I see that as a fraction, a ratio, so that must be a rational function. It goes on to say that if x is replaced with the number 0, think about what we'd have. We'd have 1 over 0. The denominator is 0, which is undefined. So 0 has to be restricted from all real numbers, and we leave it out of the domain. 0 is the only number when put in for x that would make you divide by 0. I mean, I could put anything else in for x, like a negative number, positive number, anything like that. So what's the domain for this rational function? Well, we have to remove 0. So if I kind of use a number line to help me organize my work, if this is 0 and I put an open circle above this 0, that means I want to exclude x equals 0 from my domain, but yet every other number, as represented by these arrows, any other x value that's smaller than 0 or greater than 0 can be put in for this x, and I can find a value. So the domain is negative infinity up to 0, parentheses, union, and then again on the other side of 0 with the parentheses to infinity. So, and we read it as all real numbers except x equals 0. All right, I'll come back to these additional examples after we look at some graphs, these additional rational function examples when finding the domain. But just wanted to kind of give a little bit of background about rational functions. All right, same thing with even root functions. Let's look at a definition, a little bit of background. We're going to look at some graphs to help us maybe understand it more fully as well. All right, what's an even root function? Well, even meaning like square root, fourth, sixth, eighth root, not an odd root. We're going to restrict our attention really mainly to the square root, that even root. All right, so what can't we have in that kind of situation? Well, we must restrict any x value, any value of x that results in the even root of a negative number in order to stay in the set of real numbers. Just a quick reminder, if I have the square root, that even root, and I have negative 9 underneath here, well, that answer is going to be 3i. Remember, the square root of negative 1 is I, square root of 9 is 3, so that would be 3i. I is not a real number, it's an imaginary number. So we don't want any negative values to be underneath the even root or the square root. So now let's look at this equation right here. what if we have the square root of x? We're not dealing with a rational function. We don't have a fraction. But what I want to be concerned about is this value, whatever x is here, cannot be negative. So how do we find out what we can have underneath here so I can take the square root of it, and I'm taking the square root of a non-negative number? So what we do is we take what's underneath the radical, and in this case it's just x, and we say, you know what, that x, it's got to be a number that's greater than, or it could possibly be equal to 0. So what's the domain of this function? Well, any numbers. Let me draw a little number line to organize our work. Here's 0. Now above 0, I'm going to put a closed circle because x could also be equal to 0, and greater than would indicate we go this way. So our domain is 0, but we can include it, so we use a bracket and we go to infinity. All right, we're going to return to this additional example right here in a minute, but before we do that, I want to go to some graphs. So you may or may not have this in your packet, not sure. So you can just either just watch, or I'll attach it so you can print it if you need to. All right, so again, like I said, our objective is to find the domains of polynomial functions, even root functions, and rational functions. So these first three graphs right here, if you look at the equations that produce these graphs, okay, these equations are all polynomial equations. Okay, so all of these polynomial equations produce graphs where the domain is all real numbers. Then the x values of every point on this graph is negative infinity to positive infinity. There are no breaks or gaps in this graph. So all the domains here can be written as all real numbers. So I'm just going to record that below each of these equations. So the objective is going to be what happens when we pull away these graphs and all we have are these equations, and we're asked the question to find the domain. We have to be able to identify that these equations, they're not fractions, so therefore there's no rational functions. I don't see any square roots. I don't see any of these square root symbols. So these are all polynomials. So just immediately, without much thought, just record the domain to be all real numbers. All right, we'll look at even root functions. Notice that this graph actually has a starting point right here at x equals -4, and I guess y is 5. This graph has a starting point at x equals -5 up here at a height of positive 1. And this graph actually doesn't even start until x equals 3. These types of graphs that have kind of these starting points and then go off in a certain direction, okay, they're not going to be polynomial functions because the domain here isn't going to be all real numbers. There's parts, you know, of the graph that, or this graph doesn't exist over here, so I can't have negative infinity to positive infinity. So what we want to kind of look at is, I'm trying to make a connection here that this graph doesn't begin until x equals -4. Can you see where that might be found in this equation that produced this graph? Okay. As a reminder, to find the domain of an even root function, what we saw on that other sheet was it said, take what's underneath the radical, which is x plus 4, and we want to make sure that that expression, x plus 4, is not a negative number. We do not want to take the square root of a negative number. So I simply force this expression to be a number, this number, x plus 4, greater than or possibly equal to 0. So in that case, how do I solve for x? Okay, so I'm going to take the parentheses off. I don't need them. I'm going to subtract the 4 from both sides of this inequality. I'll come up here. So these 4's will cancel. So x must be greater than or equal to -4. So let's just try a few values. Try in x equals -4. You add 4, you get 0. I can take the square root of 0 and get 0. That's fine. Plug in a number bigger than -4, like -2. -2 plus 4 will return a positive number. I can take the square root of a positive number. Likewise, let's kind of do the opposite of that. Let's choose a number that's smaller than, not greater than -4, like -10. If you put -10 in for x and added 4, you're going to get -6, and you can't take the square root of a negative number and get a real answer. All right, so how would we graph this? Well, we would graph this on a number line by putting -4, closed circle. This inequality says greater than, so I'd go this way. So this domain, it reported in interval notation, would be bracket -4, comma, infinity. So let's connect that back to the graph. Does this graph right here show that the domain starts at x equals -4 and contains all other x values past greater than -4? And it does. All right, so let's look at this domain. From the graph, without looking at the equation, I see that the domain would be -5 with a bracket to infinity. Well, where can we get -5 from this equation? Because eventually we're not going to have a graph and we're going to have to rely on this equation. Well, I see that this equation is an even root function, so I kind of dial that in and I go, wait a minute, I can't have a negative underneath the radical, and everything that's underneath the radical is x plus 5. That has to be greater than or equal to 0. And the parentheses aren't necessary here, so I'll go ahead and remove them. All right, let's find values for x that would make this greater than or equal to 0. So let me subtract a 5 from both sides. So x has got to be greater than or equal to -5. And that's what I see here. X is greater than or equal to -5. And using interval notation, we would do -5 with a bracket to infinity. All right, let's look at this even root function that's produced from this equation. Well, this domain is 3 to infinity. Where can I get 3? Just think about that number 3 right now. Where can I get 3 out of this equation? Well, again, I don't want x minus 3 to be negative, so let's force it to be positive. Parentheses aren't necessary because my next thing to do here is to solve for x. So any x value number greater than or equal to 3 is going to give us the result after we subtract by 3, a positive number to take the square root of. Try it. Try a number that's smaller than 3, like 0. If you plug 0 in for x and subtract 3, you're going to get a -3 underneath the radical, and that's going to be the square root of a negative number or an imaginary number. So that doesn't work. Okay, so our domain from this equation is going to be 3 to infinity. And the graph supports it. All right, so the takeaway is, so far, polynomial functions like this, with these kinds of equations, with no radicals and no fractions, the domain is just simply all real numbers. We have a little more work to do when finding the domain of even root functions. We have to look for the radical. There it is. The 2 and the 5 have nothing, no bearing on the domain. We just want x plus 4 to be greater than or equal to 0. We solve, we find the values for x that make that true, and we can report the domain. In this example, this equation, if I want to find the domain, I ignore the 1 and the -3, but I take the x plus 5 and I force it to be positive, greater than or equal to 0, I solve. In this equation right here, we take x minus 3, set it greater than or equal to 0, solve, and we get the domain. All right, let's look at some rational functions in their graphs. So looking at these equations down here, 1, 2, 3, all 3 of these equations have fractions. So fractions think ratio, ratio think rational functions. If you go back to our notes on the first page, it tells us that we have to look for restricted values in the domain. So that's what we'll be doing in a minute. Let's first look at this graph. So the domain for this first graph right here, as suggested by the arrows, is that the domain can be all the way over here at -infinity, but when I get right here to x equals +2, I have to lift my pencil and come back up here and continue drawing. So x equals 2 is not part of my domain. Another way to think about that is if you're standing at x equals 2 and if you look up or down, I'll never connect to this graph. So x equals 2 is the only number that I need to remove from all real numbers. So I can go -infinity up to 2 and then from 2 to +infinity. So where does this 2 restriction come from in this equation? Well, again, we don't look at the numerator for the domain question. That's for something else later. We look at the denominator. We never want to divide by 0. So I would take x minus 2 and say x minus 2 cannot be, this is my way of, you could put equal to, but I'm going to put does not equal. This expression x minus 2 right here cannot be 0. All right, let's solve for x. Well, I don't need the parentheses, so x minus 2 cannot be 0. Add a 2, both sides. So we're saying that x cannot be 2, and I can see the visual here that x cannot be 2. It can't be part of my domain. So organize our work in a number line, put 2, put an open circle above 2, but represent all other numbers that I can use with those arrows. All right, so let me come up here and report the answer using interval notation. So I'm coming up from negative infinity. I conclude at 2 with the parenthesis, union, and then I start again on the other side of 2. So this domain needs to be had from this equation. It's a rational function. Set the denominator not equal to 0, solve, and you know the restricted x value. The graph supports that x equals 2 is not part of that domain. All right, let's look at this graph right here. Let's just see if we can, by inspection, by looking at the graph, see what the domain is. Well, the arrow suggests the graph goes outward, so negative infinity up to, I have to lift my pencil at x equals negative 3. If I look up or down, I can't connect to the graph, so x equals negative 3 is a restricted x value. However, on the other side of x equals negative 3, the graph does continue, but oh, here's another place. There could be many places where you have to lift your pencil. So I have to lift my pencil at x equals negative 3 and x equals 3. So where do those two values of negative 3 and 3 come from in the equation? Well, again, it's a rational function. We do not want the denominator to be 0. So we take x squared minus 9, and we go does not equal 0. Again, you can put parentheses around here, but you're going to eventually have to remove them. All right, well, how do I solve this? Well, back to our factoring or square root property, you could either factor this into the sum and difference of like terms, or you could use the square root property. Since there's no x term here, I'm going to add 9 to both sides. I'm not going to factor, I'm going to use the square root property. So x squared cannot be 9. Let's bring in the square root. It's an even root. We're going to have two solutions, so we take out the x with an absolute value. Because remember, square root undoes square. Cannot equal, do we know what the square root of 9 is? Yep, it's 3. We'll come up here. Now it's time to remove the absolute value, but we have to make the adjustment that we can have two answers. So x cannot be 3 or negative 3. So our domain, let's see if I can fit it down here, is going to exclude negative 3, which comes first, union, but then I start again at negative 3, but I have to stop at 3, positive 3, and then union 3 to infinity. And if you need to draw that number line to organize your work, then go ahead and put negative 3 and 3. Negative 3 and 3. We don't want to include them. And we have all other x values in between. Whew. All right, this graph did not show up well, but it does look something like this. It comes from negative infinity. It comes this way. It kind of takes a little bump down. It goes through the origin. Takes a little bump up, but then what it does is it follows the positive x-axis. All right, so this rational function, which comes from this equation, has no breaks in it. Sometimes that happens. Sometimes you only have one restricted x value. Sometimes you have two, could be more. Sometimes even a rational function, a fraction, doesn't produce any restrictions. This domain is all real numbers. Okay, well, let's see. Again, to find any restricted values, let's take x squared plus 1. I guess I'll have to do it up here. And let's make sure it doesn't ever equal 0, so I don't divide by 0, that won't ever be 0. Let me subtract a 1 to both sides of the equation. So I get x squared equals negative 1. So I'm going to bring in the square root, bring in the square root. As you bring in that square root above that negative number, that's an imaginary solution. So let me come up here. Square root undoes a square. It's an even root. I have the absolute value of x. This value is actually I, the imaginary unit. So even if you remove the absolute values, you're going to get positive and negative I. So if you go to a number line to try and graph that, you're never going to see I on here. So there are no numbers, real numbers, that you have to restrict from the domain. So this informs us, okay, that there are no restricted x values. I could never get 0 down here. Even if you plug in 0 and square it and add 1, you're going to get 1 down here. If you plug in a negative number for x and square it, it'll always be made positive, and then you're adding 1 more to that. this can never be equal to 0 based on that structure of that equation. So my domain is all real numbers. Hopefully connecting to graphs of these equations and then kind of looking at the equations kind of helped you understand a little bit about the domain and finding the restrictions, if there are any. Okay, so now I want to go back to the worksheet. So let's finish up looking at these domain restrictions. So polynomial functions, all real numbers. Rational functions are fractions. We look for the denominator, set the denominator not equal to 0. It's a personal choice that I set the denominator not equal to 0. Some people set it equal to 0 and then remove what they found from all real numbers. Either way, it doesn't matter. All right, so let's look at this example. All right, if this denominator contains an expression, which it does, and we're finding the domain, set the denominator equal to 0. I'm going to set it not equal to 0. 2x plus 1 not equal to 0. I'm going to subtract 1, and I end up with 2x equals negative 1. Divide both sides by 2, and I'm going to get that x cannot be negative 1/2. This is the restricted value. It has to be restricted from the domain. So negative infinity, negative 1/2, union, start again at negative 1/2, and go to infinity. All real numbers except x equals negative 1/2. All right, let's look at one that's a little more complicated, a little rational function that's a little more complicated. If the denominator contains an expression that can be factored, factor first, then set each factor equal to 0 and solve for x. Okay, my objective here, let's find the domain. What do? I focus on the denominator not equal to 0. This is a quadratic trinomial where a is 1. You could do factor by grouping, or because a is 1, I could do a quick multiply, or a factor sum chart, I think is what I called it, factor sum chart. And you can go through that whole process of factoring, and you will get these two binomials. So x minus 5 cannot be 0, and x plus 4 cannot be 0. Add a 5 to both sides, x cannot be 5. Subtract a 4 from both sides, x cannot be negative 4. Two restricted x values. It might be helpful to put these restricted x values in order on a number line, excluding them with open circles, and then filling in the other places. So it helps me go and then go right to domain. Negative infinity to negative 4, union, negative 4 to 5, union, and then 5 on to infinity. Rational functions, look at the denominator, set it not equal to 0, find your restricted x values, remove them from negative infinity to positive infinity. All right, let's go to now an even root function. So we looked at this example, now let's look at another one. All right, so if the radicand is just a word that means what's underneath the radical symbol. If what's underneath the radical called the radicand contains an expression such as this, set the expression x minus 4, this right here, everything that's underneath here, to greater than or equal to 0. Remember with the square root, you just don't want a negative number. Fractions, you don't want to divide by 0. That's how we handle that. Set the denominator not equal to 0. Even root functions, set the radicand greater than or equal to 0. So I'm going to add 4. So x must be a value greater than or equal to 4. So when I replace that 4 bigger number in here, this becomes a positive number, and I can take the square root of a positive number and get a real number. So 4 to infinity. Okay, I think we just need to do some practice problems. So let's look down here. We've got some practice problems. First thing I would say is I would say look at the equation and identify it first. So in my brain I go, okay, is that polynomial, rational, or even root? Well, it's not rational because it's not a fraction and it's not a root. It must be polynomial. The domain of a polynomial function has no restrictions. All right, 2 is a rational function. So how do we find the domain of a rational function? Well, we do not want the denominator to be 0, so we go 3x minus 2 cannot be 0. We have to solve for x to find that value to restrict, so add 2. Divide by 3. So x, I'm going to come over here, x cannot be 2/3. That's the only restricted x value. So for rational functions, we start at negative infinity and go up to that restricted x value, and then start again on the other side. All right, let's find the domain of this even root function. It's not polynomial, it's not rational. Okay, so what do we want to be mindful of and careful of? Well, we don't want to take the square root of a negative number. So let's make sure that x plus 2, that radicand, is greater than or equal to 0. So I don't need the parentheses because there's no operation to be performed, so I can just subtract a 2 to both sides. So x must be greater than or equal to negative 2. So negative 2 to infinity. This one's kind of weird because it starts with a bracket, whereas these other two don't, polynomial and rational. They start with parentheses with the infinities on the bookends, the left and right side. Okay, I think we have a few more examples of domain. Yeah, we've got 3 more, so let's look at these. All right, even root, rational, rational. Darn it, there's not any polynomials just to say all real numbers and we're done. All right, so on number 4, it's even root. So let's take the radicand, make sure it's not negative. So that whole expression must be greater than or equal to 0. Don't need the parentheses. Let's add a 27 to both sides to save some room. I'm just going to mentally add 27 to both sides. So I'll get 9x greater than or equal to 27. And then I'm going to divide by 9. You can show the division by 9. But when you divide by 9, you're going to get x greater than or equal to 3. So using interval notation, the domain is 3 up to infinity. Feel free at any time to stop the video. If you want to attempt them on your own, that's the best way to kind of, cement that learning. All right, 5 and 6, they're both rational functions, so our eyes should land on the denominator only for the domain question. X squared plus 4 cannot be 0. Subtract a 4, subtract a 4. X squared equals negative 4. You're going to bring in the square root. You might as well just stop here and bail out of the problem because that's going to be an imaginary solution, which tells us that there are no restricted x values, no restrictions on x. Only imaginary numbers. So no restrictions means your domain is all real numbers. Rational function, can't divide by 0 for the domain question. It's a quadratic trinomial. We can do that factor sum chart. Okay, or you could do grouping. But when A is 1, you can kind of get right to the 2 binomials. So factors of A times C, which is 8, that have to sum to 6, or B. So we've got 1 and 8 and 2 and 4. Both numbers have to be positive, so it has to be this right here, this set of factors. So x plus 2 and x plus 4. Set each factor does not equal to 0 and solve. So x plus 2 cannot be 0. X plus 4 cannot be 0. So from this factor, x cannot be negative 2. If I subtracted 2 to both sides, and if I subtracted 4, x cannot be negative 4. It always helps me if I take these numbers, because with the negative numbers, I gotta always remember negative 4 is to the left of negative 2. It's smaller. Otherwise, I'd get those out of order. And then hopefully from here we can just report the answer using interval notation. All right, so that concludes that topic of domain when we looked at polynomial, rational, and even root functions. Okay, in the next video, we'll just continue with the remainder of the content.